the aircraft that flew faster than the bullets fired to shoot it down. During its entire operational career, more than 1,000 missiles were launched at it, not one connected. Tonight is the story of how that was possible. Before we continue, just wanted to let you know that we have heard your feedback and we're now on Spotify. Go through the link in the description to join us there for a rich listening experience. Walk into the right museum gallery and you will find it waiting. The SR-71 Blackbird does not announce itself the way most museum objects do. It is not behind glass. It is not roped off at a significant distance. In most of the facilities where a surviving example is displayed, you can walk directly beneath it, close enough to place your hand on the landing gear if no one stops you, close enough to look up at the underside of the fuselage and watch the play of the light on a surface that is darker than almost anything you will encounter in ordinary life. Not black in the way that a painted wall is black. Black in the way that something designed to absorb and radiate heat at extreme temperatures looks when it is sitting still in a room with fluorescent lighting and schoolchildren walking past. The aircraft is 107 feet long. That is almost exactly as long as a 10-story building is tall, laid horizontal. It stands 18 feet high at the tail, which is tall enough that the vertical stabilizers catch the light near the ceiling of most hangars it occupies. The wingspan is 55 feet. These are large numbers, but they do not fully prepare you for the specific experience of standing beneath the thing, looking up at the chined forebody and the twin-engine nacelles and the strange, swept-back elegance of a shape designed not for beauty, but for sustained flight at 3 times the speed of sound, in an atmosphere that would tear most aircraft apart at those velocities. The SR-71 Blackbird holds the official absolute speed record for a crewed air-breathing aircraft, 2,193.167 miles per hour, set on July 28, 1976. That is Mach 3.32, roughly 36 miles per minute, a speed at which the aircraft covered the distance from New York to London in 1 hour, 54 minutes, and 56 seconds. These records were set nearly 50 years ago and have not been approached by any crewed aircraft since. Not because no one has tried, because the physics of what the SR-71 did were, and remain, extraordinarily demanding, and no program has since found a reason compelling enough to attempt what Kelly Johnson's team at Lockheed accomplished in the early 1960s. The aircraft entered service with the United States Air Force in January 1966 and was primarily retired in 1990, with a brief reactivation from 1995 to 1999. In that operational life, spanning more than 2 decades of Cold War reconnaissance missions over some of the most heavily defended airspace on Earth, not a single SR-71 was ever lost to enemy action. No missile ever connected. Over North Vietnam alone, the North Vietnamese military fired approximately 800 surface-to-air missiles at SR-71s during the war. The count of total missiles fired at SR-71s across its entire career exceeds 1,000. The aircraft's response to every one of them was the same: push the throttles forward and fly away faster than the missile could follow. The story behind how this was possible starts in 1960, with a missile that did connect with a different aircraft at a different altitude on a morning in May above central Russia. That morning set in motion a chain of decisions that produced the Blackbird, the requirement that emerged from a single, catastrophic event, the engineer who answered it, the secret facility where the work was done, the material that almost couldn't be obtained, the fuel invented specifically for this one aircraft, the engines that remade themselves at speed, the pilots who wore suits borrowed from the astronaut program to sit in cockpits where the windows grew too hot to touch from inside. Tonight traces the full arc of all of it, moving from that Russian morning in 1960 to an airstrip in California in March 1990, where the last Blackbird to fly on an operational mission broke 4 speed records on the way to the museum where it now sits. 20 chapters, None of them in a hurry, each one quieter and slower than the one before it. The aircraft in the museum does not move. It has not moved under its own power since 1990, for the ones that made their final flights then, or 1999, for the last ones that flew at all. But it remains, in the specific category of what it was built to do, unchallenged. No one has replaced it. No one has surpassed it. The museum lighting catches the dark surface of the fuselage and finds almost nothing to reflect. That quality, the way it absorbs rather than returns the light around it, is as good a place as any to begin. To understand why the SR-71 exists, you have to start with an aircraft that was shot down, and the morning it happened, and the chain of consequences that followed from a single surface-to-air missile connecting with its target above the Central Soviet Union on May 1, 1960. The aircraft was a U-2, a high-altitude reconnaissance plane designed for the Central Intelligence Agency by Kelly Johnson and his team at Lockheed's Secret Skunk Works division. The U-2 was, by any measure, a remarkable machine. A glider with a jet engine, built with an enormous wingspan and a very small, very light airframe, capable of reaching altitudes above 70,000 feet, heights that were, in the mid-1950s, when the design was first produced, believed to be well beyond the reach of any Soviet surface-to-air missile system. That belief had driven the U-2 program since its inception. Beginning in 1956, SR U-2s overflew Soviet territory, photographing military installations, missile sites, and other intelligence targets that ground-based methods could not reach. Soviet radar tracked these overflights, and Soviet political and military leadership were aware of them and furious about them, but for several years, the technical means to stop a U-2 did not exist. The aircraft simply flew too high. The Soviet SA-2 missile, capable of reaching approximately 70,000 feet, was at the upper limit of its engagement envelope when attempting to intercept a U-2, and early attempts to bring one down had failed. On the morning of May 1, 1960, the gap closed. A SR U-2, flown by Francis Gary Powers, was on a mission to overfly Soviet territory from Pakistan to Norway, photographing Soviet missile facilities along the route. Near the city of Sverdlovsk, in the Ural Mountains region of central Russia, a Soviet SA-2 battery fired a volley of missiles. One of them detonated close enough to the U-2 to damage it severely, and the aircraft went into an uncontrolled descent. Powers bailed out at lower altitude and was captured. The political consequences were immediate and severe. The Soviets had proof, in the form of the downed aircraft and its captured pilot, that the United States had been systematically overflying Soviet territory for years. Soviet Premier Nikita Khrushchev used the incident to humiliate President Eisenhower publicly, cancelling a scheduled summit meeting in Paris and demanding an apology the United States would not issue. Powers was tried in Moscow, convicted of espionage, and sentenced to 10 years, though he was exchanged in February 1962 for a Soviet intelligence operative named Rudolf Abel on the Glienicke Bridge in West Berlin. The intelligence lesson was as significant as the political one. The U-2 had been protected entirely by altitude, and altitude had proven insufficient. The Soviets had improved their missiles to the point where the gap between what the U-2 could reach and what a Soviet SA-2 could reach had effectively closed. If the United States wanted to continue overflying Soviet territory with manned reconnaissance aircraft, it needed something fundamentally different. An aircraft that could not be intercepted, not because it flew too high for missiles to reach, but because it flew too fast for them to catch. The requirement that emerged from this analysis was daunting. A surface-to-air missile travels at between Mach 2 and Mach 3.5, depending on the type. An aircraft that can outrun an intercepting missile needs to be operating at speeds close to or exceeding those figures before a missile has a chance to close the gap between its launch point and the aircraft's position. This meant an aircraft capable of sustained cruise at Mach 3 or better, combined with altitude high enough that the missile's climb time further reduced the engagement window. No aircraft of any kind had sustained those speeds before. The engineering to produce one did not exist yet. The CIA's request landed, as the U-2 program had, at Lockheed's Skunk Works in Burbank, California. The man who would lead the response to it was the same man who had designed the U-2 in the first place, which meant the person assigned to build an aircraft that couldn't be shot down was the same person whose previous aircraft had just been shot down. Kelly Johnson had not designed an aircraft that failed. He had designed an aircraft that had succeeded, exceeded its expected operational life, and been caught only when the missiles improved enough to close the gap he had designed into the original specification. His response to being given the problem of the closed gap was the same as his response to every engineering challenge he had ever faced. Identify the fundamental constraint, find the simplest solution that addresses it, and build it as quickly as possible. What he built this time would be unlike anything he had built before, unlike anything anyone had built before, and it would require him to solve problems in engineering, materials science, and propulsion that had no existing answers. He would have to invent the answers. That process, and the kind of mind capable of it, is the next part of the story. Clarence Kelly Johnson was born in 1910 in Ishpeming, Michigan, and from early childhood showed an unusual gift for seeing the way air moved around objects. This is not a metaphor. The people who worked alongside Johnson at Lockheed over his 4-decade career described him as capable of performing complex aerodynamic calculations almost instantaneously, with an accuracy that formally trained engineers using conventional methods would confirm only after hours of subsequent analysis. He could visualize, with what appeared to be genuine 3-dimensional precision, how airflow would behave around a shape that did not yet exist outside his mind. He joined Lockheed in 1933 and spent the next several decades demonstrating, repeatedly, and sometimes in conditions of extreme time pressure, what this gift could produce. The P-38 Lightning, a distinctive twin-boom fighter that broke the 400 mph barrier without jet engines, carried his design work. The P-80 Shooting Star, America's first operational jet aircraft, was designed and built in 143 days. The F-104 Starfighter was the first aircraft to simultaneously hold the world speed and altitude records. The U-2, the aircraft that would eventually be shot down over Sverdlovsk and make the SR-71 necessary, was his design as well. These are the publicly known names. Behind them ran a parallel body of work, classified and inaccessible to most aviation historians even decades after the fact, that represented some of Johnson's most significant engineering, produced under the conditions that allowed him to work at his best: minimal oversight, maximum talent, strict secrecy, and a clear operational requirement to answer as quickly as possible. The organization that produced this work was Lockheed's Advanced Development Projects Division, universally known by a nickname that came from a whiskey still in the Lyle Abner comic strip, the Skunk Works. Johnson ran the Skunk Works according to a set of 14 operating rules that he developed and refined over the course of his career. They emphasized small teams of talented engineers who were empowered to make decisions and avoid the overhead that large programs accumulated. They insisted on direct communication between the design team and the customer, with minimum interference from organizational layers on either side. They required that the customer's representative be present at the facility with enough authority to approve design changes on the spot, and they assumed that the program would be held to strict cost and schedule discipline, with the customer paying for what was needed and not for what was comfortable. Johnson's summary of his design philosophy was the KISS principle: keep it simple, stupid. Applied to aircraft, this meant that every feature of a design should serve a clear, necessary function, that complexity should be avoided wherever simplicity could serve the same purpose, and that the best engineering solution to any problem was usually the most direct one, not the most elaborate. The Skunk Works operated under these principles with a staff that was, by design, small. Johnson maintained that a group of a few dozen talented people working under clear direction could accomplish more than a group of hundreds working under layered management. The U-2 had been designed and built in 8 months by a team of this kind. The results justified the method. Johnson's reputation within Lockheed was that of someone simultaneously difficult and brilliant, demanding and irreplaceable. He expected from his engineers the same clarity of thinking he brought himself, and he had limited patience for imprecision in either calculation or communication. He was also, by the accounts of the people who worked for and with him, genuinely committed to the success of the aircraft his team produced, not as an abstract engineering achievement, but as a functioning machine that would perform its mission without killing the people who flew it. His aircraft had excellent safety records. This was not accidental. Lockheed's corporate leadership, aware of what Johnson produced and what he meant to the company's most important programs, offered him the presidency of Lockheed on 3 separate occasions. He turned the position down each time, preferring to remain at the Skunk Works, doing the work that the Skunk Works did, rather than ascending to a role that would have taken him out of that environment. The presidency of an aircraft company held, for Kelly Johnson, less appeal than the chance to design the next aircraft. When the requirement for a successor to the U-2 arrived after the Powers shootdown in 1960, the assignment went to Johnson and the Skunk Works, with what was, by the standards of any normal procurement process, an extraordinary expectation. They were to produce an aircraft capable of sustained flight at Mach 3, at altitudes above 80,000 feet, with a radar cross-section smaller than any previous aircraft, in a time frame that would make the resulting machine operationally available before the strategic gap left by the U-2's vulnerability became critical. Johnson accepted the requirement. His notes from the early Archangel design series, the series of conceptual designs that eventually produced the A-12, and from there the SR-71, show a mind moving through problem space at speed, eliminating approaches that could not work, and converging on the approaches that could, with the same efficiency that he was designing into the aircraft itself. Everything about what came next was, as he would eventually say about the entire SR-71 program, something that had to be invented. Every part, every process, every solution to every problem the design encountered, none of it existed yet. Johnson's design process for the A-12 began with a series of conceptual iterations he called the Archangel series, each one designated by a number, Archangel 1, Archangel 2, and so on, through a sequence of proposals that each addressed the fundamental requirement in a different way, and each revealed why the previous approach did not quite work. The 12th design in the series was selected. The designation A-12, later understood by the public as a mysterious alphanumeric label, was simply the project name for the 12th Archangel. What that design produced was an aircraft unlike anything that had flown before it. The A-12 was slim, with a narrow fuselage designed to minimize cross-sectional area and drag at extreme speeds. Its forward fuselage featured what Johnson called chines, angled blending surfaces, that ran from the nose along the sides of the aircraft to the engine nacelles, giving the forward section a distinctive flattened shape when viewed from the front. 2 engines sat in nacelles mounted on the outer wing, swept back at an angle that contributed to both the aircraft's aerodynamic performance and its reduced radar cross-section. The design looked, from most angles, like something drawn by someone who had been told to make an aircraft as uncomfortable for radar as possible, and had taken that instruction seriously. The CIA operated the A-12 under a program called Oxcart. Testing began at a remote facility in the Nevada desert, a dry lake bed about 90 miles north of Las Vegas, on land controlled by the Atomic Energy Commission, and accessible only through a network of classified clearances and restricted airspace. The location was designated Groom Lake, on maps that almost no one saw. It would eventually become known to the public as Area 51, a designation that accumulated decades of speculation and rumor about what was happening there. Much of it significantly more dramatic than the actual answer. Highly advanced aircraft, tested in secret, by engineers and pilots who were not allowed to discuss their work with their families or friends. The A-12 made its first flight on April 25, 1962. It was piloted by Lockheed test pilot Lou Schalk, and the flight was brief, covering a low-level pass across the length of the lake bed before landing. The aircraft's development through 1962 and 1963 verified what Johnson's calculations had predicted. The A-12 could sustain Mach 3 flight at high altitude, making it the first aircraft in history capable of this performance in production form. It also proved, in the process, that designing the aircraft was only half the engineering challenge. Operating it required solutions to problems in fuel chemistry, engine management, materials processing, and airframe thermal management that no one had needed to solve before, because no one had previously built a production aircraft that would be exposed to those conditions on a regular basis. The A-12 had another characteristic that would become increasingly important over the following decades. It was the first production aircraft designed with deliberate stealth features incorporated from the beginning. The chined forebody, the angled surfaces, and the specific materials chosen for certain sections of the aircraft all contributed to a radar cross-section significantly smaller than that of a conventionally shaped aircraft of comparable size. The A-12 was not invisible to radar, but it was substantially harder to track and to generate a reliable firing solution against than anything that preceded it. SR A-12 missions from 1967 onward included overflights of North Vietnam and operations in the Western Pacific related to North Korean activities. The aircraft's operational record included no losses to enemy action, a record consistent with the requirement that had driven its design. The Air Force, watching the A-12 program with considerable interest, wanted its own version. What they needed was an aircraft capable of carrying more fuel, operating longer missions, and supporting a crew of 2, with the second crew member dedicated to managing the advanced reconnaissance sensors the Air Force required. The resulting design was larger, longer, and heavier than the A-12, and it was designated SR-71. Lockheed signed the contract to build it on December 28, 1962. The SR-71 first flew on December 22, 1964. The two aircraft were visually similar, and the engineering principles underlying them were shared. But the SR-71 was larger in every dimension, built to carry the full weight of the reconnaissance mission in a platform that the Air Force would operate in its own right, rather than supporting a CIA program. It was also, as the programs evolved, the aircraft that would eventually become public in a way the A-12 never quite was, revealed by President Johnson in July 1964, with a statement that described its existence in broad terms while the specific capabilities remained classified. The shape that Johnson's design team had refined across those Archangel iterations was now committed to 2 production programs, each of them operating at the outer edge of what physical materials could endure. And the material those shapes were built from was a problem that required a solution as unusual as anything else in the program. The problem that defined everything about the SR-71's construction was heat, and the heat came from a fact of physics that cannot be engineered around, only managed. When an aircraft moves through air at high speed, the air in front of the aircraft cannot get out of the way quickly enough to simply part and let the aircraft pass. It compresses, and compressed air heats. At the speeds that subsonic aircraft fly, this heating is measurable but modest, and standard aluminum alloys handle it without difficulty. At Mach 3, it is a different category of problem. The leading edges, nose cone, and large surface areas of an aircraft cruising at Mach 3.2 experience aerodynamic heating that raises skin temperatures to levels that aluminum cannot survive. Aluminum begins losing structural strength at temperatures above roughly 250 degrees Fahrenheit. It has essentially failed as a structural material long before it melts. At Mach 3, the surface temperature of the SR-71's skin averages above 600 degrees Fahrenheit across the airframe. Above the engine nacelles, where the engines themselves add heat to the already intense aerodynamic heating, temperatures exceed 1000 degrees Fahrenheit. The nose cone and leading edges encounter sustained temperatures that aluminum would fail at within minutes of reaching operating speed. An aluminum SR-71, even if one could be built, would destroy itself in flight. The material that Johnson's team selected was titanium. Titanium is stronger than aluminum, lighter than steel, and capable of withstanding sustained temperatures far beyond the range where aluminum becomes unusable. It is also, under conditions of normal manufacturing in the early 1960s, extraordinarily difficult to work with. The metal is brittle in ways that conventional machining techniques do not handle well. It reacts badly with common cutting fluids and lubricants. It is sensitive to contamination during processing in ways that require careful attention to the entire manufacturing environment. The learning curve for working with titanium at the scale required for the SR-71 program was steep and unforgiving. The result of selecting titanium as the primary structural material was an airframe that is, by weight, approximately 85% titanium and titanium alloys, with the remaining structure composed of polymer composite materials chosen partly for their own heat resistance and partly for their contribution to reducing the aircraft's radar cross-section. Every structural member, every skin panel, every load-bearing element of the SR-71 is either titanium or the composite material that fills a specific function that titanium alone cannot serve. The cockpit presented its own particular thermal challenge. The pilots and RSOs who flew the SR-71 needed to be able to see outside the aircraft, which meant the cockpit required windows. Windows in a vehicle whose skin reaches 600 degrees Fahrenheit must be capable of containing a pressurized environment on one side while facing extreme external temperatures on the other, without failing mechanically or transmitting so much heat inward that the crew compartment becomes unlivable. The solution was laminated quartz glass in panes approximately 1.25 to 2 inches thick, depending on the specific window location, chosen for its combination of thermal resistance, optical clarity, and structural integrity under the combined loads of pressure differential and aerodynamic heating. Even with quartz glass of this thickness, the window surface visible from inside the cockpit was hot to the touch at cruise conditions. SR-71 pilots and RSOs reported that a gloved hand placed against the interior surface of the windscreen would register significant heat within seconds, enough to be uncomfortable through a flying glove in a few seconds of contact. The same quartz that felt hot to a gloved hand inside was facing temperatures outside that conventional glass would have failed at, cracked, or distorted beyond the optical tolerances that reconnaissance photography required. The thermal management challenge extended to systems and components inside the airframe as well: hydraulic fluid, electrical wiring insulation, fuel system components, sensor housings, and the structural attachments holding the various systems in place, all had to function correctly across a temperature range that extended from the frigid conditions at altitude before the aircraft reached cruise speed to the sustained heat of Mach 3 cruise. Materials science, in the early 1960s, had not been asked to produce components for this environment before, because no environment of this kind had existed in a production aircraft. Many of the solutions developed specifically for the SR-71 program were the first time anyone had solved that specific problem in that specific way. The titanium itself was available in the quantities required for the SR-71 program from a relatively small number of global sources. Johnson's team, having determined that titanium was the only viable structural material, found that this particular fact about the world's titanium supply created a problem with an irony so specific that it has defined how the program is remembered as much as anything else about it. The problem was where the titanium came from. In the early 1960s, the Soviet Union controlled the majority of the world's accessible supply of the rutile ore, from which aerospace-grade titanium is produced. The United States had some domestic titanium capacity, but not enough to meet the SR-71 program's requirements, without supplementing it with imports. The primary available source of those imports was the country the SR-71 was being built to spy on. The CIA's solution was to establish a network of shell companies and third-party buyers, operating through intermediaries in countries with no direct connection to the United States defense industry, to covertly purchase Soviet titanium and route it into the Lockheed supply chain. The operation proceeded without Soviet awareness. Moscow's government was the primary supplier of the raw material for an aircraft being built specifically to penetrate Soviet airspace at altitudes and speeds Soviet defenses could not match. The Soviets were, in the most literal sense, helping to build the aircraft that would eventually photograph their most sensitive military installations. The irony of this arrangement was recognized within the program and noted, sometimes with appreciation for its particular quality, by the engineers and officials who knew about it. Ben Rich, who would eventually succeed Kelly Johnson as head of the Skunk Works and who wrote a widely read account of his time there, described the titanium sourcing as one of the more remarkable aspects of a program that contained many remarkable aspects. The transaction was not illegal under any framework that governed US-Soviet relations at the time, since it was conducted entirely through third parties in neutral countries, but it was extraordinary as a Cold War intelligence operation that served industrial rather than informational purposes. The titanium once obtained created its own set of problems that the acquisition had not resolved. Working with titanium at the scale required for the SR-71 proved genuinely difficult in ways that the Skunk Works team had not fully anticipated from the available technical literature. The metal's behavior under machining, forming, and joining was different from aluminum in ways that required new techniques throughout the manufacturing process. The tools used to cut and shape conventional aerospace-grade aluminum were typically made from hardened steel with cadmium plating, a standard finish that prevented corrosion and extended tool life. When these tools contacted titanium, the cadmium reacted with the titanium's crystal structure and caused the material to crack. The discovery of this reaction cost the program significant quantities of material before the cause was understood, and the tool supply was replaced with unplated titanium tools specially fabricated for the program. The expense and delay involved in this single discovery was representative of the broader experience of manufacturing a material that the aerospace industry had never worked with at production scale before. Quality control presented a parallel challenge. Early batches of Soviet-sourced titanium that arrived at Lockheed contained metallurgical contamination at rates that required rejection of a significant fraction of the material. In some batches, over 80% of what was delivered. The contamination was not consistent or easily predictable from external inspection, requiring testing of individual billets before they could be committed to components. Managing the titanium supply, ensuring consistent quality, and maintaining the schedule of the manufacturing program required engineering and logistics effort that was itself a substantial fraction of the total program management burden. The solutions to all of these problems were, in each case, specific to the SR-71 program and developed without precedent to draw on. New testing protocols for incoming titanium, new manufacturing processes for forming and joining titanium at the tolerances required, new heat treatment procedures to produce the material properties the design required in finished components, new quality control techniques to verify those properties had been achieved before the component was committed to an assembly. As Ben Rich summarized the experience, the program had to build not just an aircraft, but the industrial capability to produce it. from a material that the industry had not previously needed to master. By the time the SR-71 was in production, Lockheed had, effectively and involuntarily, become one of the world's leading experts on working with titanium. This expertise found application in subsequent programs, both within Lockheed and, as the specific techniques were eventually declassified or independently developed by other manufacturers, in the broader aerospace industry. The SR-71 program is often described as having advanced the state-of-the-art in titanium metallurgy by a decade or more relative to what the industry would have achieved without the specific, pressurized requirements of a program that needed the material and had no alternative. The titanium, once obtained and processed into components, had to be assembled into an airframe. The specific way that assembly was done and the specific consequence of how it was done that every crew chief and ground handler learned on their first day with the aircraft is the next part of this story. Every SR-71 that ever sat on a runway before a mission leaked fuel. This was not a maintenance problem. It was not a manufacturing defect, or a sign of an aircraft in poor condition, or something the ground crew was supposed to fix before the aircraft could fly. It was a consequence of a deliberate engineering decision, and understanding why the decision was made requires understanding what happens to titanium when it gets very hot. Metal expands when heated. Every metal does this, to a degree determined by that metal's thermal expansion coefficient, a number that describes how much a given length of the material will grow for every degree of temperature rise. Titanium's thermal expansion coefficient is relatively low compared to aluminum, which is one of the reasons it was chosen for an airframe that would be subjected to sustained high temperatures. But low is not zero. At the temperatures the SR-71 reached at operating speed, the aircraft's titanium structure expanded measurably across every dimension, including its length. The aircraft was, in a literal and measurable sense, longer at Mach 3.2 cruise than it was sitting on the ramp before takeoff. The skin panels that formed the walls of the aircraft's fuel tanks were built with gaps between them at room temperature. These gaps existed because the engineers who designed the airframe knew that when the aircraft reached operating temperature, the thermal expansion of the titanium would close those gaps, pressing the panels together and sealing the tanks against leakage. At room temperature, those gaps were open. Fuel, which was loaded into the tanks before flight, found its way through those gaps and onto the ramp below the aircraft. The ground crews who worked with the SR-71 did so in an environment where fuel was continuously present on the ramp surface. This was simply the operating reality of the aircraft. The pools beneath it were not small. Photographs of SR-71s on the ramp prior to flight often show visible streaking of fuel across the underside of the fuselage and the wing roots where the gaps were largest and the fuel flow was greatest. A conventional aircraft leaking fuel on the ramp would represent a serious fire hazard, and work would stop until the leak was identified and repaired. The SR-71 presented a different situation. The fuel it leaked, a specialized compound designated JP7, had properties that made the pooling on the ramp safe to work around, for reasons that will be addressed in the next chapter. The ground crews were trained to understand why the leaks occurred and what properties made them acceptable, and they worked around the pools as a normal part of preparing the aircraft for flight. The alternative to building the aircraft with these gaps would have been to seal the panels tightly at room temperature, which would have produced the correct configuration for ground handling, but the wrong configuration at operating speed. Thermal expansion at Mach 3 temperatures would have forced the sealed panels against each other with pressures large enough to buckle, crack, or permanently deform the structure. The choice was between an aircraft that leaked fuel on the ground or an aircraft that failed structurally in flight. The engineers chose the option that was safe, which was the leaking one. The expansion dynamic affected more than the fuel tanks. The aircraft's entire length increased during flight. The forward fuselage, the landing gear bay, the leading edges, the engine nacelles. Every component of the structure grew at the rates determined by titanium's thermal expansion coefficient across the temperature difference between the hangar and Mark III crews. Aircraft that returned from missions were measured for dimensional changes from their ground-level configuration, and the data confirmed that the engineering models of thermal expansion behavior were accurate to the tolerances required. The mathematics that predicted the aircraft's behavior in this respect were verified by the physical reality of the aircraft's performance. Pilots who flew the SR-71 were briefed on the dimensional changes during aircraft qualification training, and the specific effect on cockpit geometry was something they experienced directly. The cockpit structure moved slightly as the aircraft heated, and the fit of the canopy against the fuselage changed in predictable ways as operating temperature was reached. None of this affected the aircraft's performance or safety, but it was part of the sensory experience of flying a machine that was, in a real sense, a different object at speed than it was on the ramp. The fuel pooling on the ramp below the aircraft required a fuel with properties unlike anything in the existing US military aviation inventory. Building that fuel from nothing was the next problem on the list, and solving it required a different kind of chemistry than the aerospace industry had previously needed to master for any production aircraft program. Standard military jet fuel of the 1960s was a formulation designated JP4. It worked well in conventional aircraft, was widely available, and was understood by the Air Force's maintenance and logistics systems at every level. It was also completely unsuitable for the SR-71, for a reason that became clear as soon as the engineers considered what the aircraft's fuel tanks would experience at cruise conditions. At Mach 3, the SR-71's fuel tanks are not passive storage vessels that happen to contain fuel. They are heat exchangers. The titanium skin of the aircraft absorbs aerodynamic heat from the outside and transfers it inward, and one of the primary places that heat goes is into the fuel itself. The fuel inside the tanks at cruise conditions reaches temperatures above 130 degrees Celsius before it is injected into the engines. JP4 at 130 degrees Celsius would flash boil, turning from a liquid fuel into a vapor that could not be managed by the fuel system, and that, once it reached the engine, would combust in an uncontrolled way. The fuel would, in effect, try to burn before it reached the combustion chamber, and the consequences of that inside a fuel tank would be catastrophic. A new fuel had to be developed specifically for the aircraft, with a flash point high enough that it would remain stable as a liquid across the full temperature range the tanks would experience. The result was JP7, a specialized kerosene-based fuel formulated with additives designed specifically to raise its flash point and improve its thermal stability at high temperatures. JP7's flash point was approximately 140 degrees Fahrenheit, meaning that under standard conditions, it would not ignite when a lit match was dropped into a pool of it. The match would go out. This property, which the ground crews working around fuel-soaked ramps came to rely on, was not incidental. It was the central requirement that the fuel's formulation was designed around. The same stability that made JP7 safe to pool on a ramp created its own engineering problem. An engine cannot start on a fuel that will not ignite under normal conditions. The conventional electrical spark ignition systems used in most jet engines were insufficient to ignite JP7 reliably. A different ignition method was required. The solution was a chemical compound called triethylborane, abbreviated TEB. Triethylborane is a pyrophoric substance, meaning it ignites spontaneously and instantly upon contact with air. When a metered quantity of TEB was injected into an SR-71 engine during start, it reacted with the air already present in the combustion chamber, reaching temperatures high enough to ignite the JP7 flowing into the engine. The visible sign of this process from the ground was a flash of green fire at the engine exhaust during startup, distinctive enough to be identifiable from a distance and familiar enough to the skunk works and Air Force crews who worked with the aircraft that it became one of the defining visual signatures of the SR-71 on the ground. Each of the SR-71's two engines was equipped with a sealed tank holding 600 cubic centimeters of TEB, inerted with nitrogen to prevent the compound from reacting with any oxygen inside the tank before it was needed. Each tank held enough TEB for 16 uses, which covered both initial engine start and the relighting of the afterburner multiple times during a mission. Once the 16 uses were exhausted, the engine could not be restarted in flight. This was a hard limit on mission management, and SR-71 crews and mission planners were required to account for it when planning how the engines would be operated. Supporting an aircraft that consumed JP-7 at a rate of between 36,000 and 44,000 pounds per hour at cruise required a dedicated tanker fleet unlike any other in the Air Force's inventory. Standard KC-135 tankers carried JP-4, which was incompatible with the SR-71's system. A modified variant, the KC-135Q, was developed specifically to carry JP-7 in isolated fuel tanks, with separate plumbing systems to keep the JP-7 and the tanker's own JP-4 entirely separate. The 56 KC-135Qs produced for the program existed almost entirely to support the 32 SR-71s. The ratio captures something important about the SR-71's operational reality. It required an enormous support infrastructure, almost entirely dedicated to its specific requirements, that could not be shared with other programs or other aircraft. The fuel, the ignition system, the dedicated tankers, and the specialized training required to manage all of them added a layer of complexity to SR-71 operations that had no equivalent in the rest of the Air Force's fleet. At the heart of all of this complexity were the two engines that burned the JP-7 and produced the performance that justified every extraordinary step taken to build and supply this aircraft in the first place. Those engines were, in their own right, as remarkable as anything else in the program, and what they did at high speed was something no other production aircraft engine had done before or has done since. The two engines that powered the SR-71 were designated Pratt & Whitney J58. Each one produced 32,500 pounds of thrust, with the afterburner engaged, and the pair together gave the aircraft enough power to sustain Mach 3.2 cruise while carrying its sensors, fuel, crew, and the structural weight of a titanium airframe through air that, at those speeds, was doing everything physically possible to slow the aircraft down. The J58 is formally classified as a turbojet, and that classification is accurate for the portion of the operating envelope in which it behaves like one. At takeoff and through the acceleration phase of a mission, the J58 functions as a conventional afterburning turbojet. Air enters the front intake, passes through a series of compressor stages that raise its pressure, mixes with fuel in the combustion chamber, ignites, and exits through the turbine and afterburner in the way that the basic turbojet cycle has worked since the 1940s. By Mach 1.5 or so, this is essentially the operation the engine is performing, and a pilot in this phase of flight is flying a very fast, very powerful conventional jet aircraft. What happens between approximately Mach 2.2 and the aircraft's cruise speed of Mach 3.2 is not what happens in any other production aircraft engine in the history of aviation. As the SR-71 accelerated past Mach 2.2, a system of 6 bypass ducts began opening, routing a portion of the incoming air from the front of the engine around the core turbomachinery and directly into the afterburner section at the rear. This bypassed air did not pass through the compressor stages, did not mix with fuel in the combustion section, and did not spin the turbine. It was rammed from the intake directly into the rear of the engine by the aircraft's own forward motion, where it mixed with exhaust from the core and with additional fuel injected into the afterburner, and was burned at high temperature to produce thrust. By the time the aircraft reached Mach 3, Approximately 80% of the J-58's total thrust was coming from this bypass and afterburner system, rather than from the core turbomachinery. The engine had, in operational practice, transformed itself from a turbojet into something that functioned like a ramjet while the aircraft was in flight, without any action required from the pilot. The transition happened automatically, governed by the engine's fuel control system and the inlet geometry, and the pilot's experience of it was a smooth continuation of the acceleration that had begun at lower speeds. A ramjet, for context, is a jet engine without any rotating compressor machinery. It uses the aircraft's own forward motion to ram air into a combustion chamber at sufficient pressure for combustion, a simple and elegant principle that becomes viable only at speeds above approximately Mach 2, where the dynamic pressure of the incoming air is high enough to make the process work. The J-58's bypass system exploited the same principle without abandoning the turbojet core that allowed the engine to function at lower speeds where pure ramjet operation is impossible. The result was a single engine that could start and operate at rest on the ramp, accelerate through the subsonic and supersonic regimes as a turbojet, and then shift its operating mode at high Mach numbers to take advantage of ramjet physics, all while the crew flew the aircraft without needing to manage the transition manually. At the front of each engine, nacelle sat a large, triangular inlet spike. These spikes were not fixed in position. They moved forward and backward along the engine axis, controlled by the inlet management system, adjusting their position to manage the shockwave pattern that formed in the incoming air at different speeds. At low speeds, the spike was positioned to allow maximum airflow into the engine. As the aircraft accelerated through the supersonic regime, the shockwave geometry required progressive adjustment of the spike position to maintain the correct pressure recovery and airflow conditions at the compressor face. The specific position of the spike at any given Mach number was determined by the design of the inlet system and managed automatically, another transition that occurred without pilot input in the same way the bypass system transition occurred. The J-58 consumed JP-7 at rates that varied with operating conditions, but averaged between 36,000 and 44,000 pounds per hour at cruise. This consumption rate meant that the aircraft's fuel supply, even at full capacity, was sufficient for only a few hours of Mach 3 cruise before requiring replenishment. Missions longer than the fuel supply permitted required in-flight refueling, conducted at subsonic speeds from KC-135Q tankers, with the SR-71 slowing from Mach 3 cruise to the tanker's maximum speed, accepting fuel, and then accelerating back to cruise conditions. The engine that made all of this possible, and the aircraft it powered, required crews selected and trained in ways that had more in common with spaceflight preparation than with conventional military aviation. Approximately 86 pilots and reconnaissance systems officers flew the SR-71 during its operational career. The number is small for an aircraft that served for over 2 decades and flew more than 3,500 operational missions, and it reflects the selection standard applied to SR-71 crews rather than any shortage of volunteers. The program drew candidates from the most experienced aircrew in the Air Force, then applied a further screening process that evaluated performance history, medical profile, and the specific combination of technical aptitude and operational judgment that flying this particular aircraft required. What awaited a selected crew member was, before any flight ever took place, a relationship with a piece of clothing that dominated the preparation for every sortie. SR-71 pilots and RSOs wore full pressure suits for every flight. This was not optional and not a precaution for extreme scenarios. It was a baseline requirement driven by the aircraft's operating altitude. At 85,000 feet, atmospheric pressure is so low that an unprotected person would lose consciousness within approximately 15 seconds and would face fatal physiological injury within a short period after that. A pressure suit failure at altitude was not survivable without a functioning suit to replace it. The suits were not a safety measure added to a flight that could be conducted without them. They were a prerequisite for a human being to exist in the aircraft's operating environment. The suits used in the SR-71 program were developed by the David Clark Company, and their design lineage traces directly to the pressure suits used in NASA's Gemini spacecraft program in the 1960s. Later iterations of the SR-71 suit served as the initial pressure suits for Space Shuttle approach and landing test pilots in the 1970s, and elements of the design continued to inform astronaut suit development through subsequent programs. The suits provided full-body pressure containment, integrated temperature management through water-cooled garments beneath the outer pressure layer, and communication systems built into the helmet that allowed crew communication through the mission. Putting on an SR-71 pressure suit was not a quick process. Pre-flight suit-up took approximately 30 minutes under the supervision of suit technicians who checked every seal, connection, and system before allowing the suit-up process to be marked complete. The completed suit, before the crew boarded the aircraft, underwent pre-breathing of pure oxygen to purge nitrogen from the blood and tissues, a procedure common to both astronaut preparation and SR-71 crew preparation, intended to prevent decompression sickness if the suit needed to function as the primary pressure environment rather than a backup. This pre-breathing period typically lasted about an hour. Once in the aircraft, the crew's connection to their environment was almost entirely mediated by the suit and the cockpit systems. The cockpit itself was pressurized to an equivalent altitude of approximately 26,000 feet, which is itself high enough to require oxygen supplementation and is significantly above commercial aviation pressurization levels, but substantially more manageable than the ambient conditions outside the aircraft. The suit maintained a pressure environment around the crew member at all times, so that if cockpit pressurization was lost, the suit would immediately become the primary pressure source without requiring any action from the crew. Long missions required the crew to eat and drink without removing the helmet. Water was consumed through long straws attached to sealed containers, guided into the helmet's drinking port by looking in a small mirror mounted inside the visor, since the helmet's orientation made direct view of the port impossible. Food was contained in tubes with a consistency similar to soft paste, accessed through the same helmet opening and delivered directly into the mouth. The management of these basic necessities required specific training and practice, and crews reported that the consumption of food and water during a long mission was a process that became routine only after considerable repetition. At cruise speed and altitude, the SR-71's cockpit presented the crew with an auditory environment that surprised many pilots the first time they experienced it. The two J-58 engines at full afterburner produced a sound on the ground that people described as a prolonged, thunderous roar, felt as much as heard. Inside the cockpit at 85,000 feet and Mach 3.2, the engines were far behind the aircraft and producing sound waves that were moving away from the aircraft's location much faster than at lower speeds. Pilots who flew the SR-71 consistently described the crew's environment as quiet, a quality that felt incongruous with the performance the aircraft was actually producing at that moment, but that resulted directly from the physics of being in front of the noise your own engines were making. It was in this quiet, suited, at the edge of the atmosphere, that the view from the cockpit waited. And the view from 85,000 feet at Mach 3.2 was something for which no prior flying experience prepared any crew member who encountered it for the first time. At 80,000 feet, the sky above you is the wrong color. Every pilot who flew the SR-71 noted this in some form. The sky over a conventional aircraft cruising at 35,000 or 40,000 feet is blue. The specific blue that results from sunlight scattering off the nitrogen and oxygen molecules in the lower atmosphere. From 85,000 feet, the the bulk of the atmosphere is below you rather than around you. The molecules that scatter sunlight into that familiar blue are mostly underneath the aircraft rather than between it and space. The sky above a cruising SR-71 is deep blue, darker than anything visible from commercial altitude, trending toward a darkness that is not quite black, but that has more in common with the sky as seen from the moon than with the sky as seen from a commercial airliner. Several pilots described it as blue-black. The transition from the atmosphere below to the near vacuum of near space above is visible as a gradient rather than a sharp boundary, and the gradient starts lower than most people who have not seen it would expect. At this altitude, on a clear day, the curvature of the Earth is visible to the naked eye approximately 360 degrees around the aircraft. The horizon, rather than being a flat line cutting across the field of view, is a curve, and the curve is perceptible without instrumentation or deliberate attention. It is simply there, the visible evidence that the planet is a sphere and that the pilot is high enough to see the shape of it. This is not a metaphor or an approximation. At 85,000 feet, the standard atmospheric models indicate that the maximum distance to the horizon is approximately 360 miles, and the apparent curvature of the Earth's surface is geometrically detectable by any observer who looks. Commercial aircraft at their normal cruising altitudes of 35,000 to 40,000 feet appear, from the SR-71's cruise altitude, as specks that are visible only because the atmosphere at 40,000 feet is clear enough to permit very long sight lines. They are 40,000 to 45,000 feet below, in the part of the atmosphere that still contains most of the weather, most of the cloud cover, and most of the visible air mass. They look like what they are relative to an SR-71 at altitude, much smaller machines operating in a much denser part of the atmosphere. At the SR-71's cruise speed, the aircraft covers approximately 32 miles per minute, or roughly 1 mile every 2 seconds. The specific relationship between this speed and the Earth's rotation produced an effect on certain high-latitude east to west or west to east routes that pilots described with a particular sense of the uncanny. At high latitudes, the Earth's surface rotates at a speed lower than at the equator. On some routes, an SR-71 flying in the correct direction was moving faster than the ground beneath it was rotating eastward. Locally, the sun was not rising but setting, even if the aircraft had taken off in darkness and the mission had only recently begun. The aircraft was, in terms of solar time, traveling backward, reaching an earlier local time at the destination than it had been at the departure point. No other crewed aircraft had ever produced this effect under operational conditions. The quartz windows of the cockpit, despite their thickness and their resistance to the thermal environment outside, provided the crew with a clear, panoramic view of everything described above. The design of the SR-71's cockpit, with the elevated pilot position above and ahead of the RSO, gave particularly good forward visibility compared to many military aircraft. Pilots reported being able to watch the Earth curve away from them in every direction, while simultaneously monitoring the instruments that confirmed the aircraft was flying at conditions that, until the SR-71 existed, had been considered the exclusive domain of spacecraft rather than piloted aircraft. The view, in the accounts of everyone who saw it, was the part of flying the SR-71 that most exceeded expectation. The aircraft's speed, its engineering requirements, its operational complexity, and the demands it placed on its crew were all understood before a pilot flew it for the first time, because the training program covered them in detail. The view was something that the training described but could not substitute for. The pilots who flew SR-71s, interviewed decades after their service, consistently identified the experience of the view from cruise altitude as the thing that separated the SR-71 from every other aircraft they had flown. Not the speed, not the pressure suit, not the exotic fuel chemistry. The view of the planet from 85,000 feet, at the edge of the atmosphere, moving fast enough that the Earth's own rotation was not a given. What the view revealed about the planet was available only to the crew. What the aircraft's sensors recorded about the territory below was the mission, and the mission was the reason all of the engineering existed. Every SR-71 mission began with a partial tank. This was not an oversight or a logistical compromise. It was a deliberate decision based on the physics of the aircraft's takeoff performance and the engineering limits of its braking and landing gear systems. A fully loaded SR-71 with 80,000 pounds of JP-7 aboard was heavier than the aircraft's brakes and tires could reliably stop if the takeoff needed to be aborted partway down the runway. The tires, made by BF Goodrich, were aluminum powder impregnated to help them reject heat from the airframe and inflated with nitrogen rather than air to approximately 425 pounds per square inch. They were 22-ply construction. They were not ordinary aircraft tires by any measure, but they had limits, and a fully fueled SR-71 at takeoff abort required more braking capability than the system could reliably provide. The aircraft therefore departed with approximately 40,000 pounds of fuel, roughly half of its full capacity. The takeoff was not leisurely. Within 20 seconds of the throttles advancing to takeoff power, the SR-71 had travelled 4,500 feet down the runway and reached 240 miles per hour. It climbed away from the runway and began immediately toward its first rendezvous of the mission. That rendezvous was always with a KC-135Q tanker, usually established within 15 to 20 minutes of takeoff, at a refueling altitude of approximately 26,000 feet. The SR-71 pulled up behind and below the tanker's refueling boom, matched the tanker's speed, and accepted a transfer of JP-7 that typically lasted 12 to 15 minutes and delivered 70,000 to 80,000 pounds of fuel, filling the SR-71's tanks to capacity. This was the fuel load the mission actually required. The full tanks could not be carried through the takeoff, so they were acquired in the air instead. Only after full refueling would the acceleration begin. From the tanker's altitude, the SR-71 descended slightly, pushed the throttles forward, and began climbing and accelerating toward cruise conditions. The aircraft reached 20,000 feet of altitude in less than 2 minutes from sea level, and the typical cruise altitude of 80,000 feet in approximately 17 minutes from the start of the climb. The acceleration to Mach 3.2 cruise followed the altitude gain, with the aircraft reaching cruise speed and altitude in a relatively smooth, continuous climb, and acceleration that the flight manual described as a gradual rather than dramatic process, particularly compared to the immediate impression the aircraft's performance specifications might suggest. At cruise, the mission's actual intelligence-gathering work began. The SR-71 covered approximately 32 miles per minute, which meant that a reconnaissance run over a specific area of interest might last only a few minutes while the sensors recorded continuously. For a target area that the mission planners needed to photograph or monitor electronically, the relevant question was not how long the aircraft could remain in the area, but how many times it could pass over it, and what the sensor systems could collect on each pass. A single pass at Mach 3.2 could produce a strip of imagery that covered an enormous geographic area, more than any other reconnaissance platform in use could match in comparable time. After the reconnaissance portion of the mission was complete, the aircraft decelerated and descended for the return flight. Missions of sufficient length to exhaust a significant portion of the fuel load during the reconnaissance run required a second refueling on the way home, with the same KC-135Q support aircraft repositioning to provide it. The logistics of pre-positioning tankers along the planned route, maintaining radio silence where the mission required it, and ensuring the timing of the rendezvous was compatible with the SR-71's fuel state required mission planning effort, that was itself a substantial fraction of the total mission work. Landing the SR-71 was its own particular event. The approach speed was approximately 175 knots, fast by the standards of most aircraft, and the aircraft deployed a large orange drag chute at touchdown to assist in deceleration. With the drag chute functioning, the aircraft came to a stop in approximately 5,000 feet of runway. Without it, the landing roll extended to approximately 10,000 feet. The chute was visible from considerable distances and became one of the more distinctive elements of watching an SR-71 land at a base where local residents were accustomed to the aircraft's presence. What the aircraft had collected during the mission, the photographic imagery and electronic intelligence gathered at 85,000 feet and Mach 3.2, was the reason every other element of the program existed. And what the intelligence showed from the beginning of the SR-71's operational career through its 2 decades of service was sometimes strategically significant in ways that extended well beyond normal reconnaissance operations, including at least one occasion when imagery provided directly by SR-71 missions contributed to the resolution of an active armed conflict between major powers. Every SR-71 mission began with a partial tank. This was not an oversight or a logistical compromise. It was a deliberate decision based on the physics of the aircraft's takeoff performance and the engineering limits of its braking and landing gear systems. A fully loaded SR-71 with 80,000 pounds of JP-7 aboard was heavier than the aircraft's brakes and tires could reliably stop if the takeoff needed to be aborted partway down the runway. The tires, made by B.F. Goodrich, were aluminum powder impregnated to help them reject heat from the airframe and inflated with nitrogen rather than air to approximately 425 pounds per square inch. They were 22-ply construction. They were not ordinary aircraft tires by any measure, but they had limits, and a fully fueled SR-71 at takeoff abort required more braking capability than the system could reliably provide. The aircraft therefore departed with approximately 40,000 pounds of fuel, roughly half of its full capacity. The takeoff was not leisurely. Within 20 seconds of the throttles advancing to takeoff power, the SR-71 had traveled 4,500 feet down the runway and reached 240 miles per hour. It climbed away from the runway and began immediately toward its first rendezvous of the mission. That rendezvous was always with a KC-135Q tanker, usually established within 15 to 20 minutes of takeoff, at a refueling altitude of approximately 26,000 feet. The SR-71 pulled up behind and below the tanker's refueling boom, matched the tanker's speed, and accepted a transfer of JP-7 that typically lasted 12 to 15 minutes and delivered 70,000 to 80,000 pounds of fuel, filling the SR-71's tanks to capacity. This was the fuel load the mission actually required. The full tanks could not be carried through the takeoff, so they were acquired in the air instead. Only after full refueling would the acceleration begin. From the tanker's altitude, the SR-71 descended slightly, pushed the throttles forward, and began climbing and accelerating toward cruise conditions. The aircraft reached 20,000 feet of altitude in less than 2 minutes from sea level, and the typical cruise altitude of 80,000 feet in approximately 17 minutes from the start of the climb. The acceleration to Mach 3.2 cruise followed the altitude gain, with the aircraft reaching cruise speed and altitude in a relatively smooth, continuous climb and acceleration that the flight manual described as a gradual rather than dramatic process, particularly compared to the immediate impression the aircraft's performance specifications might suggest. At cruise, the mission's actual intelligence gathering work began. The SR-71 covered approximately 32 miles per minute, which meant that a reconnaissance run over a specific area of interest might last only a few minutes while the sensors recorded continuously. For a target area that the mission planners needed to photograph or monitor electronically, the relevant question was not how long the aircraft could remain in the area, but how many times it could pass over it, and what the sensor systems could collect on each pass. A single pass at Mach 3.2 could produce a strip of imagery that covered an enormous geographic area, more than any other reconnaissance platform in use could match in comparable time. After the reconnaissance portion of the mission was complete, the aircraft decelerated and descended for the return flight. Missions of sufficient length to exhaust a significant portion of the fuel load during the reconnaissance run required a second refueling on the way home, with the same KC-135Q support aircraft repositioning to provide it. The logistics of pre-positioning tankers along the planned route, maintaining radio silence where the mission required it, and ensuring the timing of the rendezvous was compatible with the SR-71's fuel state required mission planning effort, that was itself a substantial fraction of the total mission work. Landing the SR-71 was its own particular event. The approach speed was approximately 175 knots, fast by the standards of most aircraft, and the aircraft deployed a large orange drag chute at touchdown to assist in deceleration. With the drag chute functioning, the aircraft came to a stop in approximately 5,000 feet of runway. Without it, the landing roll extended to approximately 10,000 feet. The chute was visible from considerable distances and became one of the more distinctive elements of watching an SR-71 land at a base where local residents were accustomed to the aircraft's presence. What the aircraft had collected during the mission, the photographic imagery and electronic intelligence gathered at 85,000 feet and Mach 3.2, was the reason every other element of the program existed. And what the intelligence showed, from the beginning of the SR-71's operational career through its 2 decades of service, was sometimes strategically significant in ways that extended well beyond normal reconnaissance operations, including at least one occasion when imagery provided directly by SR-71 missions contributed to the resolution of an active armed conflict between major powers. The calculation is this. A surface-to-air missile detecting an SR-71 at cruise speed first needs to solve a targeting problem. It needs to determine where the aircraft will be when the missile reaches altitude, not where it is at the moment of launch. This is called a lead calculation, and every surface-to-air missile guidance system performs it. The inputs are the aircraft's current position, its speed, its altitude, its heading, and whatever assumptions the guidance system makes about those parameters remaining constant long enough for the missile to intercept. At Mach 3.2, an SR-71 covers 32 miles per minute. The time for a surface-to-air missile to climb to 85,000 feet, even for the fastest available Soviet systems, was measured in tens of seconds to over a minute, depending on the specific missile and its engagement geometry. In that time, the SR-71 moved a very long distance from the point where the guidance system had computed it would be during the intercept calculation. The target was already somewhere else. The missile arrived at the calculated intercept point to find empty sky, and without a target to guide on, it detonated in empty air or self-destructed. The electronic countermeasures suite aboard the SR-71, among the most advanced of its era, added a further complication for missile guidance systems attempting to lock on. The SR-71's countermeasures could jam the radar guidance signals that many Soviet surface-to-air missiles depended on for terminal guidance, reducing the quality of the guidance solution even for missiles that had managed to be launched on a trajectory that was geometrically close to the correct intercept. Between the aircraft's speed and its countermeasures, the missile's guidance system was attempting to track a target it could barely see that was moving faster than its intercept solution could account for. The operational instruction for an SR-71 crew that detected a missile launch was simple. Push the throttles forward and accelerate. This was not a complicated maneuver. There was no jinking, no defensive turn, no flares or chaff, no change of heading. The crew acknowledged the threat, advanced the throttles, gained speed and altitude, and flew away from the engagement. The physics did the rest. Over North Vietnam during the Vietnam War, the North Vietnamese military fired approximately 800 surface-to-air missiles at SR-71s over the course of the conflict. Every pilot and RSO who flew over North Vietnam during those years was aware of the launches because the aircraft's warning systems detected them and several crews reported missiles that passed close enough to be visible on instruments or, in at least one case, to approach within 150 yards without guidance sufficient to connect. None of them connected. Across the SR-71's entire operational career, from 1966 through 1990, the total count of surface-to-air missiles fired at the aircraft exceeded 1,000 by the accounts of the crews and the intelligence records available. The count of SR-71s downed by enemy action remained zero throughout the program's life. There was one occasion on which an SR-71 was pushed to speeds beyond its normal operating parameters by a missile threat, and it is notable primarily because it demonstrates the aircraft's performance ceiling was higher than its regular operating specifications. On April 15, 1986, during U.S. military operations related to airstrikes on Libya, pilot Brian Schule flew an SR-71 at a speed in excess of Mach 3.5 to evade a missile launched at the aircraft over Libya. The aircraft performed without difficulty at a speed above the design cruise condition. It was, in retrospect, a data point about the SR-71's actual capabilities rather than its nominal ones. Kelly Johnson, describing the evasion philosophy that drove the SR-71's design, was characteristically direct about what it meant. The aircraft's defense was its speed, and its speed was sufficient. There was no need for weapons when a departure at full power placed the aircraft outside any missile's reach within seconds of the threat being detected. The design choice was made at the beginning of the program and remained valid through the program's end. Build something fast enough that shooting at it is an exercise in futility. The nature of the SR-71's untouchability produced, in the crews who flew it, an unusual operational confidence. They were flying over some of the most heavily defended airspace in the world, in some cases deliberately and knowingly, and the threat environment was real and documented and not taken lightly. But the response to that threat was the same in every case, and the response had always worked. At a certain point, having pushed the throttles forward in response to a launch detection and watched the aircraft simply leave the threat behind, the confidence in the machine's capability became simply a fact of experience rather than a matter of faith. The community that formed around this experience, at a specific base on a specific island in the Pacific, gave itself a name. In 1968, the SR-71 program extended its operational reach to the Pacific when a detachment of aircraft was deployed to Kadena Air Base on the island of Okinawa, Japan, placing the Blackbirds within range of North Vietnam, North Korea, and significant portions of the Soviet Union's Pacific military infrastructure. The detachment operated under classified cover designations that changed over the years, but the SR-71s themselves were visible to anyone on the base and to a substantial portion of the local Okinawan population who could observe flight operations from outside the base perimeter. The Okinawan Islands are home to a species of pit viper known as the habu, Protobothrops flavoviridis, a snake found throughout the Ryukyu Islands that has been part of local culture and mythology for as long as Okinawans have inhabited the archipelago. The habu is not a large snake by the standards of the world's most impressive serpents, but it is distinctive in its proportions. A large, flat, triangular head, narrowing sharply to a relatively slender body, with a silhouette that, when observed from certain angles, bears a resemblance that some observers noticed to the SR-71's forward fuselage. The wide, flat nose section of the SR-71, narrowing at the chined sides to the slimmer fuselage behind it, looked, from the right angle and with some imagination, like the head and body of a habu. The nickname was adopted. SR-71s at Kadena became habus. The crews who flew them became habu crews. The ground personnel who maintained them, the tanker crews who refueled them, and the intelligence specialists who processed their take were part of the habu community in a broader sense that encompassed everyone whose work revolved around the aircraft's operations from Okinawa. The name spread to other bases and eventually became, within the closed world of the SR-71 program, the most common informal designation for the aircraft itself, used in parallel with Blackbird, and in some contexts more readily than the official designation. The world the Habu community inhabited was defined by two characteristics that shaped everything about it. It was secret, and it was small. The classification requirements of the SR-71 program meant that crews and maintainers could not discuss their work outside the cleared community. What they did at Kadena, where they went when they went there, and what they brought back, could not be shared with family members, with colleagues in other units, or with the general military community. The operational cover maintained at Kadena required that the specific missions being flown be protected even from people at the base who had reasons to know the aircraft was there and operating, but no need to know where it had been or why. The smallness of the community produced a closeness of a particular kind. When the total population of people who know and do the same secret work is small, the relationships within that population are different from those that form in larger organizations. Crews and maintainers who flew and maintained SR-71s at Kadena in any given year numbered in the dozens rather than the hundreds. Everyone in the detachment knew everyone else, understood their specific contribution to the operation, and shared the operational experience of sending an aircraft over some of the most contested airspace in the world, and watching it come back each time, carrying intelligence that no other asset could have provided. The aircraft itself became something that people in the program spoke about with a particular regard that was different from how crew members typically discussed their aircraft in other programs. This may have been a function of the SR-71's performance, which was sufficiently extraordinary that working with it on a daily basis produced a constant awareness of its capabilities. Or it may have been a function of the program's secrecy, which concentrated experience and loyalty within a small group and produced the kind of institutional identity that forms in environments where people share knowledge that most of the world does not have access to. The habu snake on Okinawa is not considered a friendly animal. It is venomous, quick, and has a reputation on the island that has made it a subject of caution and respect among people who encounter it. The crews who adopted the name did not seem to find the comparison to a venomous snake unwelcoming. An aircraft that responded to a surface-to-air missile by accelerating away faster than the missile could follow did not need to be compared to something gentle. What it did need, eventually, was to have its achievements officially documented in the record books. And the records it set were set with the particular deliberateness of a program that knew exactly what it was capable of, had been operating at those capabilities for years, in conditions that produced no witnesses, and finally had the opportunity to demonstrate to the world what had been true for over a decade. On July 28, 1976, an SR-71A was flown over a course measured by the FAI, the Fédération Aéronautique Internationale, which governs the certification of aviation records, and produced two numbers that have not been exceeded since. The speed record, 2,193.167 miles per hour, Mach 3.32. The altitude record for horizontal flight, 85,068.997 feet. Both were set on the same day by the same aircraft, in what was a deliberate record attempt rather than a mission incidentally producing record performance, and both were certified by the International Aviation Body with jurisdiction over such things. The numbers appeared in the record books in 1976, and they are still in the record books now, half a century later, because no crewed air-breathing aircraft has since exceeded them. The specific precision of the numbers reflects the FAI's certification methodology. The speed run was conducted over a measured course at altitude, with timing accurate enough to produce a result to 3 decimal places. The altitude record was verified by the aircraft's onboard instruments and confirmed by FAI observers. The aircraft performing these runs was not, by SR-71 standards, being operated at its absolute limit. Pilots who flew the SR-71 described the 1976 record runs as involving normal operating conditions at the aircraft's established cruise parameters. The records were not achieved by pushing the aircraft beyond what it regularly did on operational missions. They were achieved by doing exactly what the aircraft routinely did, in a measured and certified way. The transatlantic record is older. On September 1, 1974, an SR-71 flew from New York to London in 1 hour, 54 minutes, and 56 seconds, averaging a speed of approximately 1,806 miles per hour over the North Atlantic. The London to Los Angeles leg, which included a stop but was certified as a record for that route combination, was completed in 3 hours 47 minutes and 39 seconds. These records also remain unbroken, and the New York to London time in particular has remained the standard against which every subsequent transatlantic aviation achievement has been measured. The nature of these records, their persistence over decades, during which aviation technology has advanced in many other respects, raises a question that is worth addressing directly. Why has no one tried to break them? The SR-71 held these records at retirement in 1990. They continued to stand through the 1990s, the 2000s, the 2010s, and into the 2020s. No other production aircraft in the interval has approached the speed or altitude numbers from 1976. The answer is that no one has built an aircraft capable of approaching the SR-71's performance envelope since the SR-71 itself was retired, because no program has had a reason compelling enough to justify the cost of doing so. Sustained Mach 3 flight in a crewed air-breathing aircraft requires the same exotic fuels, specialized engines, titanium construction, and dedicated support infrastructure in 2026 that it required in 1966. The physics have not changed, the materials have improved, but the fundamental engineering challenges of flying a human being at Mach 3 for sustained periods remain as demanding as they were when Kelly Johnson's team solved them. A program designed to break the SR-71's records would need to solve, again, the same set of problems the SR-71 program solved the first time, at a cost and complexity that no peacetime government or private entity has found sufficient reason to bear. The records therefore stand not because no one could break them, but because no one has had a sufficient reason to try. They are not aspirational benchmarks that successive generations of aircraft have been approaching. They are a line in a record book that nothing else in aviation has moved toward, in the 6 decades since the aircraft that set them first flew. The nearest competitor in speed for a crewed air-breathing aircraft remains the aircraft that came before the SR-71, the A-12 Oxcart, also designed by Kelly Johnson and the Skunk Works, whose performance specs were close, but not equal to the SR-71's certified records. The second fastest crewed air-breathing aircraft in history and the fastest are from the same program, the same designer, and roughly the same era. No aircraft from any decade since has placed in that competition at all. At cruise speed, the SR-71 moved at 0.61 miles per second, or roughly the distance from one end of a city block to the other every time your heart beat. If you drove a car at the speed limit, the SR-71 at cruise would travel as far in a second as that car would in slightly over 2 minutes. These are not numbers that suggest a record waiting to be broken. They suggest a record that is waiting out a very long pause in the history of crewed aircraft speed. The man who made those numbers possible died in December 1990. 9 months after the aircraft he designed took its final operational flight. Kelly Johnson retired from Lockheed in 1975 after 42 years with the company. But retirement did not mean disengagement. He continued consulting for Lockheed and Boeing, remained a presence in the aviation community, and followed the continuing operations of the aircraft he had designed. with the attentiveness of someone who had not stopped caring about how they performed, simply because his formal working relationship with the programs had ended. The aircraft he had designed that were still flying after his retirement included the U-2, which continued in service and which would still be flying decades later, and the SR-71, which continued operations at Beale Air Force Base in California and Kadena Air Base in Okinawa into the late 1980s. Johnson tracked the SR-71's operational record and was familiar with the performance data that came out of missions in the years after his retirement. The aircraft was performing in sustained operation as the engineering he had produced predicted it would. That specific correspondence between the mathematics of a design and the behavior of a physical aircraft in the world was, for Johnson, the central satisfaction of the work he had spent his career doing. When people asked him to describe what it felt like to watch an SR-71 fly, he is reported to have said something that was typical of the directness people who knew him associated with his personality, that it looked like it was going where it was supposed to go, and that this was everything he needed from it. He received in 1964 the Medal of Freedom, one of the highest civilian honors the United States government can award. He received the National Security Medal for his contributions to the intelligence collection programs that the Skunk Works had produced for the CIA and the Air Force. He held honorary doctorates from the University of Michigan and the California Institute of Technology. These recognitions accumulated across his career and reflected the assessment of the U.S. government and the aerospace community that what Kelly Johnson had produced at the Skunk Works represented an extraordinary and irreplaceable contribution to American national security. The person who succeeded him as head of the Skunk Works was Ben Rich, who had worked under Johnson on the SR-71 program and who eventually led the development of the F-117 Nighthawk, the first operational stealth aircraft, continuing the Skunk Works tradition of producing revolutionary aircraft under classification and pressure. Rich wrote a memoir of his time at the Skunk Works that has become one of the most widely read accounts of classified aerospace development, and in it he credited Johnson repeatedly as the foundational influence on everything the Skunk Works produced during Rich's own leadership. The design philosophy, the operating rules, the relationship between a small, talented team and an important classified customer, all of it was Kelly Johnson's creation, refined into an institution that outlasted him. Johnson's health declined through the late 1980s. He suffered a series of strokes that reduced his physical capabilities without diminishing his intellectual engagement with aviation affairs. Those who visited him during this period described him as remaining sharp in his assessment of technical questions even when his mobility was severely limited. He continued following aviation developments, read about new programs and new designs, and maintained opinions about the directions the industry was taking that his visitors found as clearly articulated as ever, even as the physical consequences of the strokes accumulated. Kelly Johnson died on December 21, 1990. He was 80 years old. The cause was the series of strokes he had suffered over the preceding years. The timing is specific. The final operational SR-71 mission had taken place on March 6, 1990, 9 months before Johnson's death. The aircraft he had been asked to design in response to the 1960 shoot-down of his U-2 had completed its operational career and flown itself to the Smithsonian, and had set 4 speed records on the way there, all before Johnson died. He knew the program had ended. He had known for some time that it was ending. What he knew about what the SR-71 had accomplished over its operational career is harder to fully assess, given how much of that record remained classified when he died and remains classified today. What he could assess from the public record was that the aircraft had done what he had designed it to do: fly over denied territory at speeds and altitudes that prevented interception, collect intelligence, and return to base, repeatedly and without loss to enemy action, for 24 years of operational service. Everything had to be invented. Everything, he had said about the SR-71 program early in his retirement years. In one of the interviews he gave looking back at the program, he died having invented it and having watched it work for a quarter century. The aircraft he designed is still the fastest, in the only category that matters, the fastest crewed air-breathing jet ever to enter service, a record set by something he drew and built from materials that had to be sourced in secret from the country his aircraft was designed to spy on, burning fuel that required chemistry that didn't exist before he needed it, powered by engines that remade themselves at speed to take advantage of a physical principle that no production aircraft had previously exploited in this way. The Air Force formally retired the SR-71 program in January 1990, citing cost and the availability of reconnaissance satellites to assume the strategic collection mission. The budget required to operate the SR-71 fleet, including the 56 aircraft KC-135Q tanker support fleet, the specialized maintenance infrastructure, the crew training program, and the processing and analysis capabilities needed to use the intelligence it collected, had grown to a level that Air Force leadership considered indefensible in a post-Cold War budget environment where the pressures driving the original program were, if not gone, at least reduced. The final operational flight of an SR-71 was conducted on March 6, 1990. Aircraft number 617972 was tasked for a final mission with a destination of the Smithsonian Institution's National Air and Space Museum at Dulles International Airport in Virginia, where it would be delivered as a museum exhibit. The crew assigned to fly it was Lieutenant Colonel Ed Yielding as pilot and Lieutenant Colonel Joseph Vida as reconnaissance systems officer. They had a choice about how to make the trip, and they chose the one that would be remembered. Between Palmdale, California, where the aircraft was based for its final missions, and Dulles International Airport in Virginia, lay roughly 2,300 miles of American geography. Yielding and Vida flew it at Mach 3.2. The first record fell on the West Coast leg, Los Angeles to Washington, D.C., in 64 minutes and 20 seconds at an average speed of 2,145 miles per hour. This was the coast-to-coast record. It has not been broken. The route to Dulles produced additional records in shorter segments. St. Louis to Cincinnati fell in 8 minutes and 32 seconds. Kansas City to Washington, D.C. in 25 minutes and 59 seconds. Each segment was a standalone record, certified separately, and each has endured. Aircraft 617972 landed at Dulles, taxied to the delivery area, and the crew shut down the engines for the last time. Yielding and Vita climbed down from the cockpit and were met by Smithsonian officials and Air Force personnel on the ramp. The aircraft had, in its final hour and 4 minutes of powered flight, left behind 4 speed records that would follow it into the museum, documented alongside the aircraft itself. They are still the records for those routes. They have been for over 3 decades. Aircraft 617972 was moved to the Smithsonian's National Air and Space Museum in Chantilly, Virginia, later known as the Stephen F. Udvar-Hazy Center, where it remains today in the main aviation gallery. Visitors who come to see it can stand beneath it and look up at the black titanium surface and the massive engine nacelles and the chined forebody that Kelly Johnson designed across the 12 Archangel iterations in the late 1950s. The aircraft's final mission odometer, in a sense, includes the records set on the flight to its own museum. The Air Force's retirement of the program proved, within a few years, to have been premature in some respects. The reconnaissance satellites that were offered as the operational replacement for the SR-71's mission could not respond as quickly to emerging situations, could not fly at the crew's discretion over time-sensitive targets, and lacked certain capabilities that had proven specifically valuable during the Gulf War of 1991 which began the year after the SR-71's retirement and during which the absence of a responsive high-speed reconnaissance platform was noted by operational commanders. In 1995, two SR-71s were returned to limited operational service under a congressional mandate that overrode Air Force objections. They flew again from Beale Air Force Base with refurbished systems and updated sensor packages, providing a capability that the Air Force's leadership remained reluctant to support, but that reconnaissance requirements in the 1990s continued to generate demand for. The reactivated aircraft flew until 1998, when the program was retired a second and final time. NASA continued operating two SR-71s as research platforms until October 1999, when the last SR-71 to fly under any program made its final flight. The records from March 6, 1990 did not expire when the program was reactivated or when it was retired again. They remain in the books as they were certified on the day yielding, and VIDA flew 617972 to its museum, holding the aircraft's final hour of operational flight in the only register that outlasts the programs and the aircraft and the crews themselves. Records are one of the few things in aviation that survive the aircraft they came from. The aircraft is now an exhibit. The records are still active facts about the world. They are still true, still applicable, still the answer to the question of how long it takes to fly from Los Angeles to Washington at the highest sustained speed a crewed air-breathing aircraft has achieved in the history of powered flight. 64 minutes, 20 seconds. The answer has not changed. When the SR-71 program ended, the aircraft did not simply disappear. They went to museums, to research programs, and to static display locations at the bases where they had operated, distributed across the country in a way that makes it possible, with sufficient planning and travel, to see almost every surviving example that exists. Of the 32 SR-71s built, approximately 20 survive in publicly accessible condition. The losses over the program's history came primarily from accidents during test and training flights, rather than from enemy action. The aircraft lost during the test program before operational service began, and a small number lost to mechanical failures and accidents over the decades of operation. None were lost to the missiles fired at them. The aircraft that the missiles could not catch are the ones that are in the museums. The ones that were lost are the ones that had accidents with themselves, with weather, with the exceptional demands of operating an aircraft at the edge of what the materials and engineering of any era could sustain. The ratio is not a bad one for a program that operated at the absolute frontier of performance for over 2 decades. The survivors are spread across the country. The National Air and Space Museum's Stephen F. Udvar Hazy Center in Chantilly, Virginia, houses aircraft 617972, the one that made the final operational flight, the one that held 64 minutes and 20 seconds from Los Angeles to Washington. The National Museum of the United States Air Force at Wright-Patterson Air Force Base in Ohio has one. The California Science Center in Los Angeles, which also houses the Space Shuttle Endeavour, has one. The Strategic Air Command and Aerospace Museum in Ashland, Nebraska, has one. The Intrepid Sea Air and Space Museum in New York has one. Beale Air Force Base in California, the primary home base of SR-71 operations throughout the aircraft's service life, has one on static display at the base entrance. Each of these aircraft has its own specific history within the SR-71 program, its own record of missions flown, maintenance cycles completed, and crew members who flew it. Some have their individual histories partially documented in declassified records. Others remain primarily defined by their individual tail numbers and the broad outlines of when they were built and where they served. The specific missions they flew, in most cases, remain classified. After the Air Force's 1990 retirement, NASA retained 2 SR-71As, tail numbers 61-7980 and 61-7971, for research purposes at the Dryden Flight Research Center at Edwards Air Force Base in California, now known as the Armstrong Flight Research Center. These aircraft flew in support of NASA research programs that used the SR-71's unique combination of speed and altitude as a research platform rather than an intelligence collection asset. The research included propulsion experiments, sonic boom characterization studies, and operational testing of sensors and systems developed for other programs that benefited from validation at Mach 3 conditions. One of the more unusual experiments conducted on the NASA SR-71 involved a linear aerospike rocket engine, a type of engine designed for the X-33 Advanced Technology Demonstrator, a prototype for a potential space shuttle replacement that was under development in the late 1990s. The linear aerospike engine was mounted on the SR-71 to test its performance at conditions that ground facilities could not replicate, using the research aircraft's speed and altitude to simulate flight conditions relevant to the X-33's planned operating environment. The final NASA SR-71 flight took place in October 1999. After that flight, both research aircraft were retired to museum display, ending the SR-71's operational life definitively after a period that spanned from the A-12 Oxcart's first flight in 1962 through 3.5 decades of continuous operation under one program designation or another. The aircraft that began as the CIA's secret answer to the 1960 shootdown had flown, in one form or another, for 37 years before the last example ever powered by its own engines came to rest. The museums now, the records still in the books. The aircraft that stand in those museums are the same physical objects they were on the days they last flew. The same titanium alloy in the same configurations, the same quartz glass still set in the same cockpit frames, the same engine nacelles that once housed J-58s spinning at the speeds required to transform from turbojets to ramjets in flight. They carry the marks of their service, the maintenance access panels, the subtle surface differences between repainted areas and original finish, the landing gear struts that compressed under takeoff loads measured in tens of thousands of pounds. They do not move under their own power. They absorb the light around them in the way they always have, and they look like exactly what they are: the fastest crewed aircraft ever to enter service, in the places where things go when they are finished, but still worth keeping. Go back to the museum gallery. Stand beneath it again. The aircraft has not moved. It will not move. The quartz glass that was too hot to touch from inside the cockpit at Mach 3 is at room temperature now, cool if you could reach it. The engine nacelles that once contained J-58 turbojets, remaking themselves into ramjets at 80,000 feet, are open to the ambient air of a building that maintains a comfortable temperature for the school children walking beneath the aircraft's wings. The titanium that was purchased in secret from the country it was designed to spy on, processed through techniques that had to be invented for this program, assembled into a structure built with deliberate gaps that pooled fuel on every ramp it ever occupied, is simply a dark surface now, absorbing the museum lighting as it absorbed radar waves and sunlight at 85,000 feet. The full story, from beginning to end. A missile rose out of the Soviet Union on May 1, 1960, and hit a U-2 over Sverdlovsk, and Francis Gary Powers survived the destruction of his aircraft and was captured, and the requirement that his shoot-down generated landed on the desk of Kelly Johnson in Burbank, California. And Johnson assembled 12 design iterations called the Archangel series, and the 12th one became the A-12 Oxcart, tested at a dry lake bed in Nevada that would eventually be called Area 51. And the A-12 proved the concept, and the Air Force wanted its own version, and that version became the SR-71, which first flew on December 22, 1964. The CIA and the Air Force bought Soviet titanium through shell companies without Moscow's knowledge to build an aircraft designed to overfly Moscow. The titanium required new tools and new manufacturing processes and new quality control methods because the industry had never worked with the material at this scale. The aircraft was assembled with gaps in its panels because thermal expansion at operating temperature would have destroyed sealed joints, and so the fuel pooled on the ramp until the aircraft got hot, and the fuel that pooled on the ramp was JP7, which would not ignite when a lit match fell into it, and the engines that burned JP7 could not be started without triethylborane, which ignited on contact with air and produced a green flash at engine start that ground crews learned to watch for from a distance. The engines at Mach 3 were running 80% of their thrust through a bypass system that had transformed them from turbojets into something closer to ramjets, a transition that happened automatically while the pilots, in Gemini-derived pressure suits, ate food through tubes and looked at the curved Earth from 85,000 feet in a sky that was deep blue-black above them and full of a view that nothing in their prior flying had prepared them for. More than 1,000 missiles were fired at this aircraft over 24 years of operational service. The evasive procedure was always the same: push the throttles forward. Not one missile connected. The aircraft appeared on radar screens across 4 continents, was tracked by some of the most sophisticated air defense networks in the world, generated diplomatic protests from governments who objected to being overflown and photographed from altitudes they could not reach, and returned to base after every mission it ever flew over denied territory. The cameras operated. The film was processed. The intelligence was delivered. On July 28, 1976, the aircraft set official world records for speed and altitude that have not been broken. On September 1, 1974, it flew from New York to London in 1 hour, 54 minutes, and 56 seconds. On March 6, 1990, the final operational flight set 4 more records on the way to the museum, including Los Angeles to Washington, D.C. in 64 minutes and 20 seconds. Kelly Johnson, who had designed the aircraft in response to a shoot-down he did not design the U-2 to survive, died on December 21, 1990, 9 months after the last flight. The aircraft outlasted him only slightly, in the sense of operational use, in the sense of what it left behind, the records that stand, and the engineering legacy, and the name of the man who produced it from an idea that had to be entirely invented. The aircraft has outlasted him considerably. It is still, in 2026, the fastest crewed air-breathing jet ever to enter service. No other aircraft has come close. The records are still accurate. The museum is open tomorrow. If tonight's long, dark, quiet journey through the story of the world's fastest aircraft has settled you somewhere calm enough to rest, this channel will be here whenever you need it next. More aircraft, more engineering, more of the specific and patient kinds of human excellence that produce things too fast, or too high, or too strange for the ordinary world to fully account for. Come back when you are ready. There is no hurry. The aircraft already went as fast as it needed to. My dear sleep science lovers, could you please say in the comments where you're watching from right now? Also, good news. Simple Sleepy Science episodes are now available for free on Spotify. Use the link in the description or on the channel profile to enjoy our stories there.